Hey there, welcome to the Williamson ether synthesis experiment at Nazareth College. In this experiment, we will be making an asymmetric ether. Remember, an ether is an oxygen that is sandwiched between two carbons. Using the named reaction of Williamson ether synthesis, we will use a haloalkane and an alkoxide as reagents in this substitution reaction, specifically SN2 reaction. In the first step of this reaction, we will take the alcohol and deprotonate it using sodium hydroxide. This deprotonated alcohol, or alkoxide ion, will now act as our nucleophile in the subsequent SN2 reaction with our alkyl halide, affording us the desired ether product. The alcohol that we will use in this reaction is paracreosol. We will use sodium hydroxide to deprotonate that to make our alkoxide ion. The alkyl halide that we are using here is 1-iodobutane. Two unique things about this experiment is that we will be heating our reaction using the microwave and that we will be using a phase transfer agent. The phase transfer agent, specifically tetrabutyl ammonium bromide, or TBAB, because our haloalkane is soluble in the organic layer and our alkoxide is soluble in the aqueous layer, we need a phase transfer agent to allow those two to mix to react. This TBAB aids the transfer of the ionic alkoxide from the aqueous layer to the organic layer where the reaction takes place. Okay, enough theory. Let's get into the laboratory. Grab a glass chem microwave reaction vessel containing a magnetic stir bar and add your 0.9 grams of paracreosol to the reaction tube. Now it's time to add 50 milligrams of our phase transfer agent, the tetrabutyl ammonium bromide. Once weighed out, add that right to the microwave vessel. Now we are going to add 5 milliliters of our 6 molar sodium hydroxide, again right to the microwave vessel. Finally, we are going to add the iodobutane. We're going to add 1 milliliter of iodobutane right to the microwave reaction vessel. We're going to mix it up a little bit, stir it just a little bit. Now take the microwave vessel and put the vent plug on top, and then go ahead and screw the cap onto the microwave vessel. Finger tighten only, please, and then hand it to your instructor. In this green reaction, we will be using the microwave to heat our sample. Once you've turned the instrument on, you can open the door and take out the turntable or the carousel and get ready to load your samples. We're going to want to use the torque wrench on our sample vial until we hear the click, and then we're going to want to place that into our carousel, our sample carousel for the microwave. Some additional requirements for this microwave is that you cannot have a total of less than 50 milliliters in all of your microwave vessels in the microwave at any given time. Additionally, the minimum volume for any given microwave vessel is 3 milliliters. Finally, once we have ensured that our samples are completely balanced within the carousel, we will place the topper or shield on, pushing the pegs into the locked position to secure all of our reaction vessels in the carousel. Once the turntable and cover are properly installed into the microwave, take the fiber optic probe that is connected to the cavity sealing and insert the end of it into the control vessel. After closing the door to the microwave, we will go to our menu screen and select Classic, and then you would go and select Williamson reaction here. The method will be loaded, and then you will see the protocol put on the screen, and then you simply have to hit the start button. From here, the microwave does all the work. You can see the carousel rotating in one direction and then the other, all while the probe is monitoring our reaction in carousel position 1. For your reference, this protocol includes a 3-minute ramp to 100 degrees Celsius, a 5-minute hold, and then a 20-minute cool down period. Once the cooling is complete, remove the carousel from the microwave and grab your sample. Unscrew the top and remove the vent plug. Notice in this one, however, because it was the reaction monitoring vessel, that we have the probe protector right there. We are going to take the contents of our reaction vessel and transfer it to a separatory funnel for extractions using diethyl ether. Now we're going to rinse out our reaction vessel with 5 milliliters of diethyl ether and add that to the separatory funnel. After proper shaking and venting, allow the layers to separate. At this point, our ether layer is on the top and our aqueous is on the bottom. So we need to remove the aqueous layer out of the bottom of the funnel into an Erlenmeyer flask. And then we are going to take that top ether layer and pour it out of the top of the funnel into an additional Erlenmeyer flask. The aqueous layer is further extracted 2 more times with 5 milliliters of diethyl ether each time. The combined organic layers are then washed with saturated sodium chloride solution and dried over sodium sulfate. We will pre-weigh a round bottom flask and then decant our product into that weighed flask, leaving the sodium sulfate behind. Oops, don't put it on the rotovap yet. Make sure that you take some of your sample and spot it on your TLC plate and your duplicate plate. The product will be spotted on spots B and C on your TLC plate. Then you can go ahead and put it on the rotovap to evaporate the solvent and collect your final product. The product is a clear, oily liquid. Here's the mass of your final product in the round bottom, and we will be doing TLC, proton NMR, and IR analysis of this final product. For this TLC analysis, we will be using a 10% ethyl acetate, 90% hexane mobile phase. Our stationary phase will be the silica gel. We will have 3 spots, and on spots A and C, we will spot our starting material, which is percresol. And on spots B and C, we will be spotting our product from the reaction. And now, safety with Jane. Subbing in for Jane is Dr. Charleboy.
Hello, students. Here are your safety precautions. Percresol is highly toxic and corrosive. Use it in the hood with gloves. 1-iodobutane is a flammable liquid and should not be used near an open flame. 6 molar sodium hydroxide is a strong base and corrosive also. When handling the microwave reaction vessel, remember that the tube may still be hot to the touch even after the appropriate cooling stage included in the protocol. And of course, dispose of all waste in the waste hood. And there you go.
There you have it. We have made an ether using Williamson ether synthesis. Congratulations. I do have to share one thing with you. The percresol smells absolutely disgusting.